Welcome back. We're continuing on with our Applied Density Altitude series. This is Sneaky Things 5, 6, and 7. So sneaky thing number 5 is that the 50-foot obstacle may not be the last one you encounter. More often, it's the obstacle that's maybe a mile or two away from the airport that's on a slight rise that pilots run into when they haven't taken it into account. Here's a sectional map containing Burns Airport out in East Oregon. And it is a high desert airport up there at 4,150 some feet. And it can get quite warm out there in the summer. So high density altitude is a kind of an everyday fact out there in Burns. And so it's important that you take a close look at the surrounding terrain. If we zoom in a little bit, we can see that Malheur Lake is at 4,098 feet, which is not a whole lot lower than Burns, but it is lower. And that's what you really need to take away, is that you need a downhill escape route. The hills off to the north are all uphill. If you head off to the north or the northeast or northwest, it's very, very flat, but it does generally, gradually get higher if you head in that direction, while it gently and generally gets lower if you head off to the south. Now there is a big power line that runs through there, and so it's important to identify things like that as well. But remember that climb gradient that we were talking about. It is quite possible, operating out of a place like Burns, to end up taking off and finding that you can't get yourself out of ground effect. And so you need to know which way to go to find a little bit lower area to turn around. And so this way will allow you to do that. You can get out here in the desert and get yourself turned around and hopefully back to the airport. Or if you feel like you just can't get back to the airport, at least find a nice flat place that you can safely put down. Here is Sun River. It's a really popular summer place to go. There's a lodge there. You can get dinner. You can actually rent a house out there really cheap and stay the weekend if you want. Typically people will take off to the south quite often on a nice day. The wind favors the south runway. And I know from experience, as you climb out to the south, that there's a very tempting little river to fly up here. But the key word is up. That river very gradually goes up here to the Wikiup Reservoir. And so it may very well on a hot day outclimb the performance that you have available in a Cessna 152 or 172. And so you may want to consider instead heading to the north, where the slope gently contours down, or at least head that direction and then make a pattern to get back down on the ground at Sun River. So that's the kind of detailed planning that is necessary in order to avoid that obstacle that's not right at the end of the runway, that obstacle that's 2 or 3 miles potentially from the runway. Sneaky things number 6 is that it's not just the takeoffs. People will often go to the high desert thinking that they'll figure out the takeoff stuff once they're there, and they'll make a determination as to whether it's going to be safe to take off. But they have to land there first. Approaches are at a higher true airspeed. Once again, we have to fly the same indicated airspeed on our approach that we always do in order to have the dynamic pressure we need on the wings to give us our lift. Otherwise, we're going to be too close to a stall. So we're flying along at our same indicated airspeed, but our true airspeed is higher. That results in a shallower descent because you're moving forward faster, but you're going down at the same speed. And it also results in a larger turn radius, as we learned when we went through the performance section. This, in turn, results in a higher percentage of go-arounds. And so you may be faced with clearing obstacles before you've had a chance to really do an analysis of where those obstacles are if you don't plan ahead. So let's take a look at this turn. I'm using the same radius of turn formula that we used when we were talking about the turn performance. We're going to start with 65 knots, which is 110 feet per second. And we plug that into our formula for a 30-degree bank turn. 30-degree bank turn is about as steep as you want to get in a traffic pattern. But what if we go from 65 knots? But what if we're at a higher density altitude? Let's say we're up at a 4,500 foot elevation strip and it's 30 degrees Celsius out, so it's a warm day. Density altitude is almost 7,200 feet on a day like that, which means our true airspeed at 65 knots is actually 72 knots. And if I plug that number into our formula, it bumps our turn radius up to 800 feet. That may not sound like much, but to scale, it looks like this. And if we are trying to line up on this runway over here, what it means is that we just blew through final, and now we have to get back over to final and get ourselves stabilized before we can tell whether we're high or low. And this whole time we've been moving faster than we're used to. So it's setting you up for a high percentage of go-arounds, much higher than you're used to. And you need to factor that in before you get to the airport while you're still in the flight planning phase. There's big repercussions for this. So this is the old power available versus power required chart. And everything in the green area here is what we have to work with for creating a climb. But what if we have full flaps out because we're trying to come in and land? The power requirement goes way, way up with those flaps out, meaning that there's only a tiny amount of climb available, or maybe none at all. Flying the 152 around, I know that at a higher density altitude, anything over really about 2,000 or 3,000 feet, if I have a full 40 degrees flaps out, there is no climb. I'm still descending at full power to maintain my airspeed. Add to all of that you're going to be touching down at a higher true airspeed when you get to the runway, and that means more energy to dissipate with your brakes. Add to that the fact that you get down there, you've botched the approach just a little bit and came in hot. You see the far end of the runway coming up fast, and so there's a big temptation to stick it down on the ground going well above a stall. Now, not only do you have a lot of extra kinetic energy to dissipate with the brakes, but the brakes don't work very well because the tires aren't making good contact with the ground. You can't pull back on the stick like you normally would, because then you'll come back off the ground again. And so you go skittering down the runway, smoking your tires, and end up in an embarrassing situation in the chain link fence at the far end. So, airplane high-density altitude approaches include a higher true airspeed, final approach overshoot, plus shallow approach angle, plus full flaps because you're desperate to get down, equal a high or hot go-around, or a runway overrun. Helicopters have to deal with a lot of the same stuff. You still have a high true airspeed, increased turning radius, decreased horsepower available for the hover when you get down there, And it adds up to a rushed approach with an increased risk of settling with power, loss of tail road effectiveness, potentially a hard landing or a rollover. Plus, with the R22 in particular, your throttle may already be wide open. You're used to having a little bit of a safety cushion down at sea level because the R22 limits the manifold pressure to a partial throttle setting. The reason they do that is so that you have that manifold pressure to a higher elevation. But at some point, you're using all the throttle to get what you normally get for manifold pressure. So what happens is, sensing the RPM drop, the governor has been gradually opening the throttle, and you're not really aware of it, and the throttle is all the way open. Now you get down close to the ground, you start coming out of effective translational lift, and the RPM starts to droop. That causes a big loss of power, and you go to roll on the throttle to compensate for it, and there's nothing there. And so you end up running out of power, coming down hard, and rolling the helicopter over. That's all of the sneaky things that I have for you, but please continue on to the applied density altitude wrap-up.